Aluminum nitride sintering furnace is the essential thermal management enabler for high-power devices, offering high thermal conductivity, excellent electrical insulation, and superior mechanical properties. From aerospace electronic packaging and AI optical communication modules to new energy vehicle inverters and 5G RF power amplifiers, wherever heat dissipation and electrical isolation are required, aluminum nitride ceramic substrates are indispensable. Vacuum sintering is a critical step in the substrate manufacturing process. The following is a direct overview of the complete process. Using a mobile transfer cart, the debound AlN green substrates are loaded into the furnace chamber. The furnace door is closed, and the multi-stage vacuum system is activated to rapidly evacuate the chamber to the ultimate vacuum level, thoroughly removing oxygen and water vapor to prevent high-temperature oxidation. The vacuum pumps are then isolated, and high-purity nitrogen gas is introduced into the chamber to achieve a slight positive pressure. The heating system is started, and the temperature is ramped up steadily to 1800 degrees Celsius following a predefined stepwise profile, with a holding time of 4 to 6 hours at the peak temperature as required by the process. During liquid phase sintering, AlN grains dissolve in the liquid phase, diffuse, and reprecipitate on grain surfaces, leading to grain coarsening and growth. Pores are eliminated through grain boundary diffusion, densification is enhanced, and finally a high thermal conductivity, highly dense AlN ceramic is obtained. At this stage, the sintering equipment's temperature control accuracy, atmosphere flow field, temperature uniformity, and thermal field erosion resistance are extremely critical. Coupled thermal fluid field optimization technology is employed to achieve furnace temperature uniformity within less than or equal to plus or minus 3 degrees Celsius, ensuring consistent performance of the ceramic products. Novel thermal field materials and a unique insulation structure enable high-precision matching between power input and temperature control, reducing overall energy consumption by 10%. After the soaking period, the furnace is allowed to cool naturally. When the temperature drops to approximately 800 degrees Celsius, the forced cooling system is activated, using circulating gas flow to significantly increase the cooling rate and shorten the production cycle, while effectively controlling grain growth to maintain stable mechanical and thermal properties of the substrates. When the furnace temperature falls below 80 degrees Celsius, a safe level, air is introduced into the chamber to restore atmospheric pressure. The furnace door is then opened, and the sintered AlN substrates are sequentially and carefully removed.